Bismillahirrahmanirrahim. Welcome back to my channel. I'm back with a video on modulation schemes. Even though I made videos, like couple of videos on modulation schemes using GNU Radio, I just want to walk you through and I want to explain these modulation schemes. What is the importance of these modulation schemes? Because I really came across with a great tool by a person. I'll leave a link to that, and then you can walk through it and you can just work it out yourself. And I'll explain what those modulation schemes is. Why do I decided to make this video now? Because I just want to give you a brief explanation of this, what modulation scheme is, because these are the key technological components in your 5G technology. I came across with this paper, Understanding 5G, and the supported modulation schemes that in 5G are going to be a variation of phase shift keying, which includes pi by 2 BPSK, QPSK, 16 QAM, 64 QAM, and 256 QAM. All of these modulation schemes are the variation of a basic digital modulation scheme, which is known as phase shift keying. You're just shifting a phase based on the data stream. All right, so that's the idea behind this. So let me just walk you through. In digital modulation scheme, you have ASK and FSK. We don't have much use of those in digital telephone or cellular telephony. But phase shift keying and the variation and different flavors of phase shift keying has found tremendous application when it comes to cellular telephony. So having that said, now we know that we have 5G supports different variation of BPSK and QPSK, QAM, 64 QAM, and 256 QAM. Let's go through this. So now this guy, Ben Sparks, I'll leave a link. He made an amazing simulations. You can just look at them and I'll explain them in a little bit. So let's say I have a pure co-sinusoidal or a sinusoidal wave. When I'm saying sinusoidal, which it could be sinusoidal, it could be co-sinusoidal. It's just interchangeable in my, when I say these. Let's say you have a data stream. Consider this is your modulating signal. It's in a form of a digital. Right now there's no signal, which means you're getting your carrier. So you think of your carrier as being a signal which is in blue. Now you're going to modulate the signal using a single. So this demo is for a single modulated 1-bit modulation. What do I mean by 1-bit modulation? For that entire cycle of the time, you're just sending a single bit. So for example, if I were to change this bit to 1, I'll leave this as 0, 0. I'll leave this as 1, 1. And then I'll leave these two guys as 0, 0. And then I'll change this to 1. So basically, the data that I'm sending is actually 1, 0, 1, 1, 0, 0, 1. So now, based on that, you will have a change in your carrier signal. This is basically binary phase shift keying. And the phase shift that you're seeing, so this is your 1. As soon as you have encountered a 0, instead of going up, it went down. So there's an 180-degree phase shift. All right, and the signal should remain as is. When you encounter 1, this is as is. When you encounter another one, you will have a same phase. Whatever the previous phase was, you're going to keep that phase. And then you encounter 0, then you have an 180-degree phase shift. And then same signal, because this is the same signal, you will get exactly the same. And then you have an 180-degree phase shift. So this is known as modulation using a single bit, or also known as phase shift keying, which we have seen previously using GNU Radio Companion. So now during this time, you were just transmitting a single bit. All right. So let me give you an analogy what we're trying to do. Let's say we want to go from here to New York, from Florida to New York. And there are 4 people. Let's say there are 7 people. 7 of these individual people are going into an individual car. This is not an efficient way of going from one place to another place. So BPSK is just like that. For every individual person, they all have to go to the same place, but they are using a different car. So for that entire bit duration of the time, you're just only transmitting a single bit. Can we do it better? Can we do anything better to it? Yes, we can. We can start adding more people in a single car. It's just like if you have instead of having just one person driving one car from your destination to from your source to your destination, you can start having more people. Start doing carpooling. I'm just to give you an analogy of it. To give you an analogy of it. So you start adding more people into your car, and then you start moving. So that leads to another modulation scheme, which is modulated single bit with 2 bits. Now, during the same cycle, during exactly the same cycle, instead of having a single bit, just like in BPSK or phase shift keying, binary phase shift keying, you start having more people. So just like a car analogy, instead of having a single person going into a single car from source to destination, now you have 2 people going into that car. So now, when you have 2 bits in a single time, in this entire time duration, how many levels you can have, how many states you can have, how many phases you can have, because 2 raised to 2 will give you 4 different phases. Now you can have 4 different phases in your diagram. So having that said, so you can set your phases from here. So you have a large data stream like 0, 1, 0, 1, 0, 1, 0, 1s. This is basically your modulating signal, information signal, which is in a form of zeros and 1. Let me change this to 0, 1, 0, 1, 1, 0, 1, 1, 0, 0. Let's leave it at 0, 1. You can change it to whatever you want, and 1, 0. Let's say, so the data stream that I have is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0. Now we're going to start modulating this using different phases, because I can have how many states, since I'm during this entire time, transmission time. Now I'm packing 2 bits, so I can have 2 raised to 2 would give me 4 states. Hence, we have 4 states. So these alpha, beta, y, and sigma, these are actually defining me the phases. So I can do it, I can change it to any phase I want, from 0 degrees all the way up to 360 degrees. So I'm going to leave this as 0, 0. Every time I encounter 0, 0, there's no change in my phase. Now, let's say I want to do QPSK with 90 degrees. So I want to change this to 90 degrees. I'll change this to 90 degrees. So check this out. So this is an amazing tool. Thanks to Ben Spark for making a beautiful tool like this. So now I'll have 0, 90 degrees. I want to give also a gap of 90 degrees. So I'm going to change this to 180 degrees now. And then I'll change this to 270 degrees. So on your circle, I'll explain this more. So every time whenever you encounter 0, 0, you're going to leave the phase as is. Now every time you encounter 0, 1 in your data stream, so now you start modulating your signal. So these numbers that you're seeing, this is actually your digital data, and this is your carrier signal. So you're changing the phases of your carrier signal based on the number of bits. So every time you have 0, 1, then your signal will jump to 90 degrees phase shift. Every time you will have 1, 0, it will, so it was on top, so you'll have a 180 degree phase shift. And every time you will see a 1, 1, you will get a 270 degrees. Okay, so you'll have 270 degrees of phase shift, and so on. So this is how you start transmitting. This is how you start encoding your bits in a form of phases. And these A, B, C, and D's, these are just showing the amplitude. That's it. They're just showing me the amplitude of your signal. That's it. Nothing else, nothing fancy going on. But the main part of understanding your modulation schemes, so this is a form of a modulation scheme which is QPSK, which means quadrature phase shift keying. Why quadrature? Because I have 4 phases. Now, there's also known as pi by 4 PSK. Pi by 4 PSK, instead of having 0, I can have this at 45 degrees. So now the constellation diagram will have a phase. Every time you encounter 0, 0, you will take a phase shift of 45 degrees. I'll explain this in a constellation diagram as well. It's easier to visualize this like this, but as the number of bits, you start packing more bits in a single time period, you need to have it in a form of a constellation diagram. I'll explain that in a little bit. So 45, so 135, I believe. Yeah, so this is going to be 135. And then I think 215 or something like that, 235. So you can basically, to get an idea, this is what it is. So 90 plus 45 will give me 135. So we have 180, 180 plus 45, so that would give me 225. So I'm giving a break of 45 degrees. So 45, 225, and then I think this is going to be 315, and this is going to be 315. So I hope you're getting an idea what I'm trying to say here. So this is how you do perform modulation. Now, this is an example of BPSK. The first example, this is an example of BPSK. This is an example of QPSK. And different variation of QPSK, you can change the phases. Now, this gets a little bit tedious because one of the key technological components is going to be your you start increasing number of phases. Eventually, so this is what's going to happen. This is what you need to notice here. Let me show you a unit circle. All right. And think of it like this. So this is your I. All right. So whenever we are working with binary numbers, whenever we're working with complex numbers, the way the phases are going to be matched. So you saw it in a form of a in a oscilloscope diagram in a previous one. But as soon as these number of state gets bigger and bigger, we plot them using something called a constellation diagram. Now, if you were to look at it, this is a unit circle. You can see the amplitude of this. So this guy is just 1. So every time I go around, the amplitude is not changing. Only the phases is changing. As you can clearly see, I go around the circle. Now, this is going to be on 90 degrees. This is going to be 180. So this is just 180. This is going to be 270. And this is going back to the original signal. So this is a unit circle that is defining 1. Now, when we were plotting BPSK, so have a look at it. Either you can have 0 degrees or either you can have 180 degrees. This is what we were seeing when we were looking at BPSK in this. Let me just go into this tab. So this is either is going to be 180 degrees, whatever that phase was, and you will get a shift of 180 degrees. So opposite. This is what we're seeing in BPSK in a constellation diagram like this. So the amplitude was changing. Eventually what will happen if I make my amplitude exactly at 1, I will run out of these phases on this. What are the number of maximum phases I can have? The maximum number of phases I can have is from 0 to 360 degrees. And we saw it in GNU radio simulation as these points are getting bigger. And how do they get bigger? When we start packing more bits. So for example, if I start packing 8 bits, 2 raised to 8 would give me 256, which means I'll have 256 point on this unit circle. Now, 1 point will be here, 1 point will be here. As soon as the noise will come in, they will start corrupting those bits. But the thing is, so they came up with a very brilliant idea. So instead of just utilizing this, why don't we utilize this space in the middle that I have available? They will definitely have a different amplitude, but I can have 1 point here, 1 point here. 1 point is having an amplitude of, let's say, 0.5 and a same phase. And the other point will be located right here. That will be exactly the same phase, but will have a different amplitude. This type of modulation is known as QAM, quadrature amplitude modulation, which is a combination of ASK and PSK combined together. Now, I hope you're understanding this. Eventually, when I start plotting on this unit circle, I will definitely run out of phases, but the space in the middle is being underutilized. So they came up with a beautiful idea of utilizing this space in the middle. Having a different amplitude but same phase would give me 2 different additional points on it. So I can also start utilizing this. This type of modulation scheme is known as QAM, QAM. And then I can increase number of levels. This is one of the key technological component in 5G technology for modulation and coding schemes. So I hope you're understanding this. So this is the background behind this constellation diagram. So this is BPSK, binary phase shifting. So either you can go here or you can go here. Now let's look at QPSK. Now when I look at my QPSK, I'm going to turn off my show BPSK. Thank you so much for Ben Spark. I appreciate it, man. This is an amazing simulation. All right. Now this is what? Now you can look at it. So 0, 0 you will see a phase like this. I believe this is 45 degrees. So then 45 plus 90 would give me 115. 45 plus 19 would give me 135. So every time you will encounter 0, 0, let me remove this. You will get 0, 0. You will get a phase shift of what? 45. Just like we did it over there in this modulation right here. 45 plus 90 is 135. So you'll get a phase shift like this. Now, every time you encounter 1, 0, you will get a phase shift of what? 135. Then 135 plus 90, that would give me 215, I believe. And then 315, 235 or 315 and something like that. So you'll get 0, 0, 1, 0, 1, 1, 0, 1. This was your QPSK. Having an amplitude of exactly what? 1. This is your I. This is going to be your in phase, and this is your quadrature. Because we work on complex numbers, this is what it is. So by changing this, you can have any angle you want on this, and you can change the amplitude of whatever you want. So every time I'm going above this, I'm getting something else. And notice this. These points on QPSK, they are definitely on unit circle. Now let's look at QAM. Let me turn this off and let's look at QAM. Now boom. Now when I look at this, check this out. So I have 16 levels. Let's count these points. 1, 2, 4 here. 1, 4, 8, 12, and 16 points. Now when I look at these 16 points, how many bits would give me 2 raised to what number would give me 16? So 2 raised to 4 would definitely give me 16 points, which means I have 16 different levels. Now when I'm encountering, now check this out. 16 QM, which means I have 16 different states. But check this out. If I were to go at this particular point, I am seeing this amplitude is looking something like 0.4 or 0.5. Exactly the same phase but different amplitude. So this thing has I value, which is an amplitude value of 0.5, having, I believe, is 45 degrees. And if I were to go here, exactly the same phase, but the amplitude was a little bit different. Amplitude is a bit higher. You're getting my point, what I'm trying to say? I hope you're understanding this. Now this is exactly half of 45. So this is my 45 degrees. Now this is exactly half of 45, so this is going to be 22.5. So 22.5, but an amplitude of 1. 45, but an amplitude of 0.5, but exactly 45 degrees phase shift, but I have an amplitude which is totally different. So you start actually utilizing the space which is available in the middle of the circle or outside of your unit circle. I hope you're getting it, which has much higher amplitude. So now you start packing more and more bits. Now instead of having 2 bits during this time, you start having 4 bits. What do I mean by that? It's just like this. Individually, you had like 7 people, 7 different cars right here. Let me go back to my analogy. So you guys were all going individually from your source to your destination in a similar car. Now what he did is this. You know what? We were doing something stupid. Why don't we carpool? Instead of having one person driving one car, let's sit 2 people. If they are going to a same destination, why don't we have carpool together and 2 people in a single car? Now, when it comes to higher modulation schemes, now we're saying, you know what? We're going to have 4 different people will be sitting in a single car. So now we're becoming more and more efficient. So during this time, you're also increasing your data rate as well. So here you were just transmitting a single bit in this time period. Now you start transmitting 2 bits in a single period, which is more effective. Definitely this is how you're increasing your data rates. That's why they use these higher modulation schemes. What? Because you start packing more bits together. Based on more bits, packing more bits, you start getting more and more data rates. So you start increasing data rates. But what was the problem that I mentioned when I was doing the simulation GNU radio? I mentioned it as when these points start increasing, what will happen to it? Whenever the noise will be there, it will start corrupting these constellation points. So the higher the modulation scheme is going to be, the noise will most likely will be able to corrupt these points. So what is the technique that 5G and these technological components in cellular telephony uses? They said, you know what? We're going to use adaptive modulation encoding schemes, which will do what? that will actually, if you're close to a base station, you're going to transmit higher data, you're going to use higher modulation schemes, so you'll get higher data rates. So because since you're close to your base station, it's more likely that noise will corrupt your signal. If you're away from your base station due to Rayleigh fading and due to different fading components, you're most likely to get corrupted. Your data most likely to get corrupted by noise. That's why they try to use lower modulation schemes like QPSK and BPSK. So that's the idea behind this modulation schemes. Thank you very much for this author for this making this brilliant simulation. If you guys have any questions, please leave it in the comment section. Don't forget to like and subscribe to my channel. And thanks for watching.